Hello Eastview Scholars, and welcome to this edition of Sharp Shorts, where we're going to take a quick look at how to write an electron configuration. And just to go back, it's based on, as we went through our views of the atom, it's based on our quantum mechanical model of the atom, which says really the changes over time was the fact that yes, there's a nucleus that contains protons and neutrons and is all the mass of the atom, but not much of the volume. Most of the volume is the electron cloud out here where the electrons are. And our difference from Bohr slightly was just that you can't pinpoint where they are, that they're not in these energy levels, that they're in these shapes, that these areas outside the electron cloud, because as Heisenberg told us, you cannot at any point pinpoint exactly where an electron is. They're constantly moving, they're constantly absorbing energy, releasing energy, and you cannot exactly pinpoint where they are. Unlike the kind of the set ring theory that he had, although his calculations for energy level distance was correct. So, but you can identify an atom from its electrons and from the 4 quantum numbers they have, and these are those right here. Quantum numbers specify the properties of atomic orbitals and the electrons in those orbitals, even though you can't pinpoint them. And no two elements will ever have the same ones. Our most important ones for writing electron configurations are really these two. The principal quantum number, which is a number right out front as we write. You'll see it's the number. All that's telling you is what row of the periodic table is it in. Okay? What's that outermost energy level, or what energy levels does it fill with electrons? The second one, the angular momentum, is within those energy levels, there's these suborbitals that it's all just kind of mathematically keeping things organized and helping define their properties. And that's the second number, and that's a letter, S, P, D, or F, which we're going to look at. The magnetic number is just as it in the X, Y, and Z axis, because these are 3D atoms or three-dimensional objects. And then the spin number just tells you, remember electrons are negatively charged, and so they will repel each other. Yet they all want to get close to the nucleus, or as close as they can get, because the nucleus is positive. So you can minimize some of that repulsion, and they can share an energy area if they're spinning in opposite directions. Anyhow, and these couple diagrams give you an idea of what they mean now. This is, you can't really tell in 3D, but it's not so much those set rings of Bohr, but these, S, P, D, F. Here's an S means sphere, so a 3D sphere around a nucleus. P kind of looks like a propeller, and you can see you have an X, Y, and Z axis, which a sphere wouldn't have because it's a sphere. Here's some D and F shapes. It doesn't really matter. The idea, though, is that we can write at what's called an electron configuration that you can use, in a sense, to identify, not always, because electron numbers can change, but it helps you identify an element or an ion if possible. And all the rules, and we'll see them in the off-ball chart, are that electrons occupy the lowest energy level they can to be as close to the nucleus as they can, but obviously the more you get, the more they build out. The Pauli exclusion principle, we mentioned already, that no two electrons can have the same exact 4 quantum numbers. They can have 3 out of 4, but never 4. And Hund's rule just says that if, like in a p orbital where you can occupy both X, Y, and Z axis, you'll fill out each axis before you go back to a new one. You'll see that as we write things here. But the other numbers I want to give to you is that if I am in an electron filling an s orbital, those are the smallest the spheres are. And so it can only hold up to 2 electrons, 1 or 2. If then I have to move on to a p suborbital for my organization, then I can hold up to 6, because I can have 2 in the x, 2 in the y, and 2 in the z orbit. D's can hold up to 10, and F's up to 14. Okay? So here we have a couple of ways to write the chart. This is little boxes by increasing energy level. And here it's the same thing, but it kind of shows you the exact order they go in, back arrow to front arrow to back arrow to front arrow, going this way. So let's just do an example. Say I have potassium, which has 19 electrons. Okay, and I know that because I look at the periodic table. It's got an atomic number 19, which means it has 19 protons by definition. But then I can assume it also has 19 electrons, and since we are just talking about a neutral atom, that would be true. Okay? So all this means is everything starts at the 1s because it wants to be close to the nucleus. So the first electron of my 19 is going to go into 1s, okay, and there it is, and I draw it as an arrow going up. The second one then will fill out the s because an s can hold up to 2, and those would be the closest to the nucleus. You know, say we put our nucleus right here, okay, that's as close as we can get. But see, now notice that the s is full. Okay, and so I've gone through 1s, I follow my arrow back here. Now I go to the 2s orbital, and again, there's the first one. Second one will spin down. I filled out the s. There's my first 4 of my 19 electrons. Now here's where Hund's rule comes in. Here's the p with its x, y, and z axis. So I'm going to put 1 electron in each. Before then, I have to fill another one. So I'm going to get 1 in each x, y, and z axis, then I'll fill it out. Now I've used 10 of my 19 electrons, and I've followed 1s, 2s, 2p or not 2p, and now I have to go to 3s. And again, 2 more will go in there. Okay. I'm up to 12, but I'm full, so I back up again. Now I go to 3p. And again, 1 in each before I spin down to minimize repulsion. Okay. And now I've used 18, and now I follow my arrow and I'm going to 4s, and I'm looking here and I'm going, wait, 3d, 4s, this is the same row, just as this was row 2, row 1 on the periodic table, row 2, row 3. Why am I not going here? Well, s is the smallest suborbital, and d is the second to largest, with f being the largest. This can hold up to 10 electrons. This can hold only 2. Well, it's going to be a whole lot less energy for the nucleus to hold on to these 2 than it is to hold these 3. That's why the squares are a little higher. It's just a little more energy, but it is more energy. And so as you notice here, after the p's, they always fill the s before they go to the d's. So my last electron goes in there, and that illustrates what my electron configuration is. And if I want to write it out, then it was 1s first, as it is with all of them, and I put 2 electrons in there. Then it was 2s, and 2 electrons went in there. And then it was 2p, and I have 6 electrons there. And then it was 3s, and again 2 electrons there. Then it was 3p, and 6 electrons went in there. And then it was 4s, and 1 electron went in there. And the thing to really note that we're looking for is that is my final, what's called my final electron configuration. So I can use that to identify where it is on the periodic table. And it's also my valence electron. So it tells me that this element has 1 valence electron, which will be very important when we talk about forming ions. Okay. Now that's all well and good, but I got a couple examples here like selenium and cesium, which has, cesium has 55 electrons. That's a lot. Notice they all start at 1s and fill out. Here's argon with its 18. They all fill out, and they all fill out. Can I do a shorthand? Yes. And that's what this noble gas configuration is called. And here's the one thing I know. Argon, xenon, and all the rest of those elements in column 18 are unreactive. They're the noble gases. They have the most stable electron arrangement, which is this 8 electrons in its outermost s and p orbitals. Okay? So they never react, they never bond because they don't want to. These are full, these are happy, they don't want to do anything. So they are the one group of elements that will never lose or gain electrons. Every other one can. In fact, the other ones do in order to simulate that. So here's what I notice. Since all elements have to start at 1s and fill out, all the way up through here, the first 18 electrons were exactly the same configuration as argon, and argon's never going to change. ever. So I can cut all this out and just say, hey, wait a minute, this was argon, the first 18. And then the rest of my 16 electrons to fill up my 34 for selenium neon, I'll just write after the argon. Same as the cesium here. The first 54 electrons through 5p6 are xenon. So instead of writing them out, I can just write out that it's xenon plus the final electron configuration here, 6s1. That's what's left over after I get to the noble gas that preceded that element. And that's the way I can crunch it down. It takes a little practice, but if you really are looking at how the periodic table is organized and how the electron configuration chart, that Aufbau chart, goes in order as it's written, then you should be able to do that rather quickly. Okay? And that's the last thing I want to point out here. If you look at this, here is a periodic table. And what you notice here is, right with their final electron configurations and their valence electrons written here, here's our S block. So row 1, 2, 3, 4, 5, 6, 7, that's the period. That's the first principal number that I write down. This is all, and S can only hold 2. Here's my S block. This is 10 across this middle section that looks unique to itself. And notice that it's all the D's. So this is the D block. So when their final configuration is written in D, and I know they're writing this one in order of period number as opposed to final electron configuration, but that's the D block. Here, these 6 across are the P's, and these 14 across are the F's, and they match how many you can fill in. Okay? So that's a quick tutorial on electron configuration. Scholar on Eastview.